Hello everyone, we are Team Energy and we did our project on energy storage methods. Our group consists of myself, Tim Cook, Ali Alhaddad, Ben Swaffar, Mattias Payne, and Tavish Thao. For our project, we considered how our systems affected the triple bottom line. We did this by examining the social, environmental, and economic aspects. The way we evaluated social was we looked at safety, convenience. The way we evaluated environmental was by examining the amount of energy saved and wasted, and considered the environmental impact. The way we evaluated economic was to evaluate the cost to run, maintain, and implement each system. For our systems considered, we compared a lead acid system. We used an SG series 750 kilovolt amp UPS system made by General Electric. We chose to use lead acid systems because they're common in the industry, have a low self-discharge rate, and have high surge currents.
For our inertial system, we chose Active Power's 750 HD UPS. We did this because it's a comparable system. For those of you who don't know what an inertial energy storage system is, it consists of a large rotating mass inside a vacuum chamber. The mass is supported by magnetic bearings and kept spinning by an electric motor. If the power goes out and electricity is needed, a generator is engaged and power is drawn off. These types of systems provide a large amount of power in a very short period of time, just enough time for a backup generator to come online.
The function of an uninterrupted power supply, also known as a UPS, is to provide seamless power in the case of a power outage. The functional unit we picked is 750 kilovolt amps. This unit could supply power to equipment for a small hospital, for example.
For our scope definition, our main focuses are initial materials the system is composed of, materials during operation and maintenance phase, energy needed during operation and maintenance phase. And for our live cost analysis, we will include the installation costs. Transportations and manufacturing phases were negligible due to their similarities.
The life cycle assessment is a framework used to examine, identify, and evaluate the energy, materials, and environmental implication of a system across its lifespan. The life cycle assessment stages includes goal and scope, inventory analysis, and impact assessment. For the inventory analysis, we build our system as shown in the gray box, which identify our boundary. Inside the gray box, we have our stages that we are considering. On the left side, we have the major inputs that goes into each stage. For example, for the raw materials extractions, the major components that goes into both systems are steel, natural gas, and sodium sulfate. We're also including operation and maintenance stage, which goes on the energy that we have to keep the system running. And for the end of life stage, we are considering reuse and recycling options. And for outputs of our system, we are considering the CO2 emissions for the carbon footprint. The life cycle impact assessment aggregates life cycle inventory data to support our interpretation of our results. The choices that we make in this stage have to consist with our scope and definition. On the left side, we can see our results from the life cycle inventory analysis. The major inputs and the outputs are natural gas and CO2. For the characterizing column, it's quantify contribution to different impact categories. For example, for natural gas, it's based on kg equivalent to total primary power. And for CO2, it's based on how many kg CO2 equivalent. For our midpoint indicators, for natural gas will lead to depletion of abiotic resources, and lead dioxide will lead to acidification, and the CO2 emissions will lead to global warming. For our endpoint impact, it will lead to damaged minerals of fossil resources and damage to human health and our damage to our ecosystem.
For our SimmerPro analysis, we assessed the embodied carbon using the IPCC 100A single issue assessment method. The life cycle stages we assessed were materials used in construction, so that includes materials needed to construct it. Note, we did not include manufacturing processes, only material processing. And then we also included operation and maintenance, so materials and parts needed during operation and maintenance, and energy needed to run the units. This graph shows the materials used in the battery UPS system over 20 years. Note that this includes battery replacements for the 20 years. This one shows the same data only for the inertial system. This shows the combination of the previous two graphs showing the breakdown of the materials used over the 20-year lifespan. Note that the battery's initial materials embody more carbon than the inertial system over the 20 years. This graph shows the total embodied emissions of each alternative, including operation energy for 20 years and embodied carbon in the materials used over 20 years. Note that the embodied carbon is insignificant to the total emissions outputs for each of the lifespans. This tells us that the electrical efficiency is most important when deciding or when trying to reduce emissions.
For the cost analysis, we analyzed the systems over a 20-year period. For the systems, we considered the cost of the system, the installation, service and maintenance, electrical costs, and replacements if necessary. In total, we found that the battery cost approximately $2 million, and for the flywheel, $1.4 million. Throwing these numbers on a chart, we can see that the battery over time accumulates more of a cost, while the inertial system increases linearly.
Shown in previous slides, the most sensitive parameter related to the output of emissions is by far the efficiency of the running unit. Well, only 1% produced a change of 500,000 kilograms of CO2 between the two life cycles. The most sensitive parameter related to the total cost is again the efficiency of the running unit and also the lifespan of the system / the batteries in this case. In the case of the battery, if the battery system fails earlier than 5 years, say 4 years, it will add another $165,000 to buy another set of batteries for this system.
For each system, there are several pros and cons that affect the triple bottom line, as listed on the slide. But in conclusion, an inertial system is better where there is a high discharge and recharge rate. And a lead-acid system is better in a long-term system due to the low discharge rate.